So today let's explore what's inside of this server power supply. It's small and compact for its power, 495 watts, in comparison to a typical computer power supply. So let's explore how it works and what's inside of it and what topology it is. Here's the label. It seems to be over 80% efficient. The input is universal mains and the output 12 volts, 41.25 amps and 12 volt standby 3 amps. Some other information here and some LED states, and don't remove unless authorized. So I can't open it, of course. Here's the fan and the mains input, and the output was here. There probably used to be a section of the board with some connector or the wires soldered in, but it's broken off, so unfortunately we are not going to be able to power it probably, but we will explore the internals. Here are some screws, so let's try to open it. 2 screws here, 2 on the other side. Some screw here, which I'm not authorized to remove. And then looking at this, it should probably slide out. And that's it. Let's take a closer look. The mains comes in here. Some interference capacitors, metal oxide varistors, Y capacitors, X capacitors, these common mode interference inductors, the fuse, some heat sinks with transistors, a lot of things on ferrites, here, transformers or inductors, some control board here, the primary smoothing capacitor, not sure what's this capacitor, these polymer capacitors at the output. I guess this small transformer will be a flyback transformer for the 12 volt 3 amp standby power supply section. This might be the power factor correction inductor, and this the main transformer. There are some other inserted board here. But let's remove the board from the box to see it better. It was on 3 screws and it comes out. Here's this insulation layer under it. Taking the fan out, it has some rubber pieces around the screws against the vibration. That's nice. And this contains the LED probably. It's probably a 2-color LED. Now it's completely out of the box, we can see it better. Here's the fan with 4 wires going to it, the LED with 2 wires. It might be 2 anti-parallel colors in it, because it talks about 2 colors here. And the board, a closer look at it. A lot of chips on this board, a control board. Another board here with something. What's this? We have to explore. Some power transistor, something with a heat sink. And the other side, some power diodes. A chip 8-pin, some power SMD resistors, probably current sensing shunts. Of course there is a lot of broken connections here, so I'm probably not powering it. There is a thermistor temperature sensor, an overheat protection or maybe to control the speed of the fan. This heat sink is for the bridge rectifier, or actually 2 bridge rectifiers in parallel. There's a relay bypassing the NTC inrush limiting thermistor here after it starts up to reduce the losses. This thing is interesting. It's one ferrite core but contains 2 windings. Is it the power factor correction inductor? Because I guess this should be the output transformer, shouldn't it? The secondary probably goes into this, the rectifying diodes. It could actually also be synchronous rectifier MOSFETs, of course. And after the rectification it goes into these output capacitors. These 3 in parallel are probably the main output. This one for the auxiliary or standby output. There are some packages, maybe MOSFETs, 3 in parallel, which can probably disconnect the power supply from the output. The load can be disconnected from this, which makes me think, is there actually a separate power supply for the standby output, or is it just one power supply and the main output is disconnected using some very low on-state resistance, low voltage MOSFETs? Both is actually possible. This could be the flyback transformer for the standby power supply, or this, or it could be just disconnecting the main output using these MOSFETs. I have to explore further. Is this isolated? This thing seems to be completely on the primary side. The isolation line actually goes through here, not under this, so it's not a transformer. So it's some sort of an inductor, I guess. Maybe it's a part of the interference suppression. Well, this could be the transformer for the standby power supply. This board should be the power supply, the standby one. This part is on the primary side. On this side, the secondary side, there's the output, I guess. This has to be the main transformer. One winding is on the primary side, and the other winding is on the secondary side. It goes to these packages, and it actually says Q. So these are transistors, not diodes. It's a synchronous rectifier for less losses. And also the small size of the heat sink of it definitely suggests it's a synchronous rectifier, not a diodes. This thing here looks like a current sensing transformer, which is probably in a series with the primary of this. Of course, this is the primary of the main transformer, and it's connected here in a series with the primary of the current sensing transformer. Now it seems these two transistors are switching the primary of this transformer, and it could be a half bridge or a two-switch forward. We have to investigate. And this is probably the transistor for the power factor correction, and here it's diode, or the other way. Another temperature sensor on this heat sink, and some temperature sensor here. Well, the power factor correction components are actually doubled. There are components on the other side of the heat sink too, so it's two transistors in parallel, two diodes in parallel. There's also one extra or two extra transistors here for the power supply. Well, one of these is diode. So outside of the power factor correction we have three transistors and one diode here. We have to identify what it does. And this thing seems to be two inductors on one core, but both in parallel. This is connected with this, and this with this. So it's used as just one inductor. And there's a big electrolytic capacitor, 270 micro, 450 volts. And the smaller one is 47 micro, and it's 500 volts. You don't see this often. You typically see on the primary side 400 volt or 450 volt capacitors, but not 500 volt capacitors. 500 volt electrolytic capacitors are quite rare. What this bloody capacitor is for, and what this inductor is for. And it's also strange, I don't see any output inductor on the secondary side. It makes me think, is it the double boost topology with no output inductor, where it has the power factor correction boost circuit, then another boost circuit after it, which could be with this inductor and this capacitor, and this actually works as the regulation for the output voltage instead of the pulse width modulation, because with no output inductor you can't have a pulse width modulation. The output voltage of this has to be regulated with no output inductor by regulating the input voltage going into the half bridge that drives the primary of this transformer. And these MOSFETs are actually the other way, not switching the output off. They're preventing a reverse current flow like synchronous polarity protection. And this has to be the standby power supply. This is the control board of the main power supply with a lot of chips on it. And two optocouplers, each of them facing a different direction, plus one special chip across the isolation line here. The detail of this control circuitry and the chips. But now let's draw a simplified schematic of this to have a rough idea what the hell is going on here. And here is the simplified schematic, not drawing the standby power supply, the control circuitry, mostly just the power components of the main power supply. The mains comes in here, there is some interference suppression, a fuse, a metal oxide resistor against overvoltage, some diodes for the startup circuitry or sensing the mains voltage. Here's the bridge rectifier, and this decoupling capacitor, but not a smoothing capacitor, probably several hundred nano. This does not smooth the voltage. There is a 100 or 120 Hz ripple, and between the half cycles the voltage goes virtually to zero. And the first section is the power factor correction. Here is the inrush diode, bypassing it for the inrush current of the smoothing capacitors, the power factor correction inductor, and the ultra-fast diode, and 2P means 2 in parallel. For simplicity I draw just one component. Here's the switching MOSFET in the power factor correction, the active one. This boosts the voltage, produces almost a unity power factor, and also roughly pre-regulates the voltage to be in the right ballpark here. Here's the inrush NTC thermistor, limiting the inrush current, then bypassed using a relay. And on this biggest electrolytic capacitor, you have probably almost 400 volts, and some partial ripple, no longer going to zero. And this stage can't get rid of the ripple completely, because at the input the voltage touches zero. Then there is the second boost stage, which looks almost the same, as the components are no longer paralleled. And this further boosts the voltage to probably something between 400 and 500 volts, and also fine regulates it. And of course each of these switching MOSFETs has a current sensing resistor in the source. And the output of the second boost stage goes into this 500 volt electrolytic capacitor. And then there is this capacitive divider with these diodes, probably preventing resonance. And this half bridge, switching the primary of the main transformer, And in a series there is this current sensing transformer. The primary is 1 turn and the secondary is rectified using a bridge of discrete ultrafast diodes, and it goes into the control circuitry. Here is the Y capacitor suppressing the common mode interference going to the output, and the secondary of the transformer has a center tap going to the positive, and these two pairs of transistors, MOSFETs, working as a synchronous rectifier. This rectifies the voltage and goes into this group of 3 capacitors in parallel, this differential mode interference suppression inductor, and another capacitor. And this group of 3 parallel SMD MOSFETs probably prevents the reverse flow of the current into the power supply. I guess these power supplies can operate in groups of several in parallel. These are super low on-state resistance MOSFETs with a built-in Schottky. And the output voltage is not regulated by changing the duty cycle of this half-bridge. It's regulated by changing the duty cycle of this transistor. These two transistors are always switching alternately, with just a minimum dead time in between. So the duty cycle of these transistors is controlled to get the power factor close to 1 in a short run, and in a long run to get the voltage here to just under 400 volts. The duty cycle of this transistor is controlled to get the voltage at the output to 12 volts, and the half-bridge probably runs at the maximum duty cycle except the startup, when the duty cycle probably gradually goes up. It has no output inductor here, but it's probably using the leakage inductance of the transformer for the startup, because otherwise this power supply is very hard to start up. And also, if you're trying to find a power supply to modify to an adjustable power supply, this is probably the worst kind of a switching power supply for this. People often modify computer power supplies the 12 volt rail to an adjustable power supply, let's say 3 to 15 volts. But here it's not possible because these stages can only convert the voltage up. Here you couldn't adjust the voltage much under 12 volts, and you also couldn't adjust it much above because then you'd exceed the voltage rating of some of these components. And I have already seen this topology in some older power supply. Here's the board from it. I kept it for parts, I already took some out of it. And it's again 2 boost stages, the inductor of the first one, second one, the half bridge, the transformer, synchronous rectifier, no output inductor, and the output. And this one actually failed. And the transistors are properly exploded here. This one and the other one. Nice. I guess the half bridge and the synchronous rectifier might actually be more efficient when it's running at the maximum duty cycle, and it's regulated by regulating the input voltage, in comparison to a pulse width modulated half bridge with the typical output inductor here, the ring. So that's it, and if you like my videos, please consider subscribing, supporting my channel on a Patreon or using the thanks button, and big thanks to all of you who already support me because this keeps my channel running.